Now let's move on to the next question, 23. Here in this question they are saying if the first and the nth term of GP are A and B. So the first term here is small a1, let's say it is given to be small a, and the last term, suppose it is an, it is given to be b, right? And they are saying if capital P represents the product of n terms. So we are supposing the n terms of the GP, they are a1, a2 up to an, so that means their product would be equal to capital P. Let's mark this as equation 1. Now we can substitute the value of each of the term here. What we need to prove? We need to prove that P square is equal to AB raised to power n. So let's see how we can do that. So here we can make use of this nth term and substitute the value of each of this a1, a2, a3, a4, a5 and so on up to an. a1 is given to be a, so you can directly put it as a. Next, the next term here would be a2. a2 by this formula, putting n is equal to 2, you have a into r, so this is your second term. Next, when you put n is equal to 3 into this formula, you would have the third term as ar raised to power 2, so this is the third term. Similarly, the nth term would be given by ar raised to power n minus 1. So here you see a is coming how many times? It is coming, there are total n terms, so it is coming n times, so we would have a raised to power small n here. And how r is coming how many times? You see here we have r raised to power 0, here we have r raised to power 1, here we have r raised to power 2, here we have r raised to power n minus 1, and they all are multiplying to each other, so that means the bases are same, so the powers would be added. So we would have r raised to power 0 plus 1 plus 2 up to n minus 1. Correct. Now this is an arithmetic progression with the first term as 0, right? These numbers form an AP with 0 as the first term and 1 as the common difference. Hence its sum would be given by n by 2 2a plus n minus 1d, right? Here AP, the first term is 0, so this term is 0. We are left with n by 2 n minus 1 times of 1, right? So this sums come out to be n by 2 n minus 1, right? This is equal to P. Let's mark this as equation 2. Now what we can do, we can just square this equation. So when you square this equation, squaring equation 2, we have, what do you have? A raised to power 2n, right? Next you have, when you square this, you would have it multiplied with 2. So this and 2 and this 2 gets cancelled. We are left with r raised to power n minus 1. This is equal to P square, right? Let's mark this as some equation number 4, say. Now moreover, we are given that the last term is equal to b. We have not made use of this thing. So because an is equal to b, so that means a r raised to power n minus 1 is equal to b. So what we can do, because you can see we wanted to prove P square is equal to a raised to power n, b raised to power n. So that means here in this expression of equation 4, we should also have some term which is b raised to power n. So that means we can here take b raised to power n. We can take power n on both sides of this equation. So that what do you have? You would have a raised to power n, r raised to power n into n minus 1, that is equal to b raised to power n. So you can clearly see, you can break this a raised to power 2n as a raised to power n into a raised to power n. This is what I have done. And now you see a raised to power n, r raised to power n minus 1. This is the same thing as this thing, which is b raised to power n. So instead of writing this thing, you may directly write b raised to power n. So clubbing these two terms together, you can write it as ab raised to power n, that is equal to P square. And this is what we wanted to prove here in this question. So I hope you understood these two questions well. Well, that is it for this video. Thank you for watching.